Imagine a boundary in space, a perfect, invisible sphere where the laws of physics as we know them are utterly and irrevocably broken. It is the point of no return, the event horizon of a black hole. Everything that crosses it, light, matter, information, and even time itself, is destined for a single, terrifying point of infinite density. Now take a moment, look up at the night sky, and consider this profound, almost unbelievable thought. What if that boundary, that event horizon, is not something far away, but something that already surrounds us? What if the entire, vast, expanding cosmos we call home, with its billions of galaxies, its cosmic microwave background, its dark energy, and every single star, planet, and living thing, is nothing more than the secret, hidden interior of a black hole existing in another, larger universe? This is not science fiction. This is a radical, yet mathematically sound, hypothesis being explored by serious physicists today. It is a theory that doesn't just challenge our understanding of black holes, but fundamentally redefines our place in reality. If you are ready to have your mind stretched to its absolute limit by the deepest cosmic mysteries, then you are in the right place. We are Cosmo Depth, and we are about to dive into the ultimate question of existence. Before we plunge past the point of no return, take a second to hit that like button and subscribe to the channel. It's the only way to ensure you don't miss our next journey into the unknown, and it helps us keep exploring these mind-bending ideas together. Our journey begins, as all great cosmic stories must, with the bedrock of modern cosmology, Albert Einstein's general theory of relativity. When Einstein unveiled this masterpiece in 1915, he didn't just give us a new theory of gravity, he gave us a new geometry for the universe. Gravity, he posited, was not a force, but a manifestation of mass and energy warping the very fabric of space-time. Think of space-time as a colossal, four-dimensional trampoline. Place a bowling ball, a star on it, and the fabric dips. A marble, a planet, rolling nearby doesn't fall towards the bowling ball. It simply follows the curve of the dip. This is the elegant geometric dance of the cosmos. But this beautiful theory contained a monster lurking within its equations. Just a year later, Karl Schwarzschild, a German physicist serving on the Russian front during World War I, found the first exact solution to Einstein's field equations. His solution described the gravitational field around a single, non-rotating, spherically symmetric mass. What he found was a mathematical boundary, a radius now known as the Schwarzschild radius, where the escape velocity equals the speed of light. Cross this boundary and you are trapped forever. This was the theoretical birth of the black hole, a concept so bizarre that even Einstein himself doubted its physical reality. The initial reaction from the scientific community was one of profound skepticism, bordering on outright rejection. The idea of a region of space where light itself could not escape seemed to violate the very spirit of physics, a kind of cosmic absurdity. Even Einstein, the architect of the theory, spent years trying to prove that such an object could not physically form. He argued that as matter collapsed, it would always find a way to stabilize before reaching the critical density, a sort of cosmic safety valve. But the mathematics were relentless, and the universe, as it turns out, is far more extreme than our intuition allows. The first crack in the wall of skepticism came in the 1930s with the brilliant work of the Indian-American astrophysicist Subrahmanyan Chandrasekhar. He proved that any star above a certain mass, now known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, must inevitably collapse under its own gravity once it exhausts its nuclear fuel. He showed that the pressure of electrons, which holds up a white dwarf star, could not withstand the crushing force of gravity beyond this limit, leading to a runaway collapse. His work was initially met with resistance, most notably from the esteemed Sir Arthur Eddington, who famously declared that there must be a law of nature to prevent a star from behaving in such an absurd way. But nature, as it turns out, is often more absurd than we can imagine. The next crucial step came from Robert Oppenheimer and his students in the late 1930s. They modeled the collapse of a massive star and confirmed that once the nuclear fuel is spent, the star collapses inexorably, crossing the event horizon and forming a singularity. Their work laid the final theoretical groundwork, but the term black hole was still decades away. It wasn't until 1967 that the American physicist John Archibald Wheeler, a master of evocative language, coined the term, giving this cosmic monster its now iconic name. The black hole was no longer a mathematical oddity. It was a physical reality, a fundamental prediction of general relativity. The subsequent decades saw a revolution in observational astronomy, with evidence pouring in from X-ray binaries, gravitational lensing, and, most recently, the direct imaging of the event horizon by the Event Horizon Telescope. We now know that black holes are not rare oddities, but a fundamental, powerful, and common feature of the cosmos. They range from stellar mass black holes, formed from the collapse of massive stars, to the colossal supermassive black holes that anchor the centers of nearly every major galaxy, including our own Milky Way, where Sagittarius A star holds sway. The sheer scale of these objects is difficult to comprehend. A supermassive black hole can contain the mass of millions or even billions of suns, compressed into a volume smaller than our solar system. Yet, despite their confirmed existence, the black hole remains the most profound challenge to our understanding of physics, and the source of this challenge lies at its very heart, the singularity. General relativity predicts that all the matter that falls into a black hole is crushed into a single point of zero volume and infinite density. At this singularity, the equations of general relativity break down entirely. They cease to describe reality, offering only a mathematical shrug. This breakdown is more than just an inconvenience. It represents a fundamental conflict in physics. The singularity is where gravity, the domain of general relativity, becomes so strong that the quantum nature of matter, the domain of quantum mechanics, can no longer be ignored. The two great pillars of modern physics, general relativity for the very large and quantum mechanics for the very small, are fundamentally incompatible at the black hole's core. This incompatibility is also the root of the infamous black hole information paradox. The information paradox is one of the deepest mysteries in physics, a cosmic conundrum that has occupied the minds of the greatest physicists for half a century. Imagine throwing a book into a black hole. The book contains a vast amount of information, the arrangement of its atoms, the specific words printed on its pages, the history of its creation. According to general relativity, once the book crosses the event horizon, it is destined for the singularity, where all its information is crushed out of existence. The black hole is defined only by its mass, charge, and angular momentum, a concept known as the no-hair theorem, famously stated as black holes have no hair. This theorem implies that all the complex information about the matter that formed the black hole is lost, leaving behind only these three simple properties. But quantum mechanics insists that information can never be truly lost, only transformed. This principle, known as unitarity, is a cornerstone of quantum theory, governing the evolution of quantum states. The paradox deepens when we consider Hawking radiation. Stephen Hawking showed that black holes are not truly black, but slowly radiate away their mass in the form of thermal particles. This radiation is purely thermal, carrying no information about the book that fell in. If the black hole eventually evaporates completely, the information is gone forever, violating unitarity. Where did the information go? If it is truly lost, it suggests that our current understanding of physics is incomplete, and that a new, more comprehensive theory is needed to describe what truly happens inside a black hole. This is the cosmic stage upon which the radical idea of black hole cosmology is set. This theory, most eloquently championed by the Polish theoretical physicist Nikodem Popławski, offers a breathtaking resolution to the singularity problem and the information paradox by proposing that the singularity is not an end, but a beginning. It suggests that the heart of a black hole is not a point of infinite destruction, but a wormhole, a bridge to a new, expanding universe. In this model, our universe is not the only one, but a baby universe, born from the collapse of a star in a parent universe. To understand how this is possible, we must first introduce a concept that Einstein's original theory omitted: torsion. General relativity describes space-time as being curved by mass and energy, a property known as curvature. The black hole cosmology model, however, is based on a more advanced theory of gravity called the Einstein-Cartan-Siyama-Kibble theory, or simply the Einstein-Cartan theory. This theory adds a second geometric property to space-time: torsion. Torsion is a measure of the twisting or spinning of space-time, and it is directly linked to the spin of matter, a fundamental property of all elementary particles. Every electron, every proton, every fundamental particle in the universe has an intrinsic angular momentum, a quantum mechanical spin. In the vast, empty stretches of space, the effects of torsion are negligible, and the Einstein-Cartan theory behaves exactly like general relativity, which is why Einstein's theory has been so successful. But in regions of extreme density, such as the interior of a black hole, the effects of torsion become dominant, and they fundamentally change the fate of collapsing matter. In the Einstein-Cartan theory, as matter collapses toward the singularity, its density increases, and the collective spin of all the particles creates an immense, repulsive force due to torsion. Imagine all the spinning particles being squeezed closer and closer together. Their individual spins begin to interact in a way that generates a powerful, outward-pushing pressure. This force acts as a kind of cosmic pressure, preventing the matter from collapsing into a singularity of infinite density. Instead of being crushed to a point, the matter reaches an extremely high but finite density, a point known as a non-singular bounce. At this bounce point, the repulsive force of torsion overwhelms the attractive force of gravity, and the matter begins to expand rapidly. This rapid explosive expansion is, in effect, a Big Bang. the birth of a new universe on the other side of the black hole's event horizon. This concept is a stroke of genius, as it elegantly solves the two greatest problems in black hole physics. First, the singularity is replaced by a non-singular bounce, meaning the laws of physics never truly break down. The infinite density is avoided, and the need for a full theory of quantum gravity at this point is simplified. Second, the information that falls into the black hole is not destroyed. It is carried through the wormhole and becomes the initial matter and energy of the new, expanding universe. The black hole, therefore, is not a cosmic dead end, but a cosmic reproductive mechanism. Every black hole in the parent universe is a potential gateway to a new baby universe, and our own universe, the one we inhabit, may have been born from a black hole in a universe that existed before ours. This is the ultimate cosmic recycling program, where the death of a star in one universe seeds the birth of an entirely new one. The information is preserved, not by being radiated away, but by being transferred to a new reality. The implications of this theory are not just theoretical. They have profound consequences for the observable properties of our own universe. If our universe is the interior of a black hole, it must possess certain characteristics that align with what we observe. And, remarkably, it does. One of the most compelling pieces of evidence is the nature of our universe's boundary, the cosmological horizon. In our universe, we can only see a certain distance, about 46 billion light-years in any direction. Beyond that, the universe is expanding away from us faster than the speed of light, meaning light from those regions will never reach us. This boundary is the cosmological horizon. Mathematically, the equations describing the cosmological horizon of our universe are strikingly similar to the equations describing the event horizon of a black hole. Both are boundaries that separate a region of space-time we can interact with from a region we cannot. In the black hole cosmology model, the cosmological horizon is simply the event horizon of the parent black hole, viewed from the inside. We are, quite literally, surrounded by the boundary of our cosmic parent. Furthermore, the theory offers a natural and elegant explanation for the flatness of our universe. Cosmological observations, particularly those of the cosmic microwave background, show that the geometry of our universe is almost perfectly flat. In the standard Big Bang model, this flatness requires a period of extremely rapid expansion in the early universe, known as cosmic inflation. While inflation is a highly successful theory, it requires the introduction of a hypothetical field, the inflaton field, and a fine-tuning of initial conditions that many physicists find unsatisfying. In the black hole cosmology model, the rapid expansion immediately following the bounce, the birth of the baby universe, naturally produces a flat geometry, potentially eliminating the need for the complex mechanism of inflation. The initial conditions are set by the collapse of the matter in the parent black hole, and the immense repulsive force of torsion drives the rapid, flat expansion. The universe is flat because it was born from a collapse that was halted by an internal, repulsive force. This is a much more organic explanation, rooted in the known properties of matter and gravity, rather than an arbitrary, hypothetical field. The theory also provides a unique and powerful perspective on dark energy, the mysterious force driving the accelerated expansion of our universe. In the Einstein-Cartan theory, the torsion field itself can contribute to the energy density of the vacuum, behaving mathematically like a cosmological constant, the very thing we call dark energy. The residual effects of the immense torsion from the bounce could be the subtle, pervasive force that is now pushing our galaxies apart. This is a far more elegant explanation than simply adding an arbitrary constant to Einstein's equations. Instead of inventing a new, unknown form of energy, the black hole cosmology model suggests that dark energy is a natural, lingering effect of the immense physics that gave birth to our universe. It is the cosmic echo of the bounce, a subtle but persistent reminder of the extreme conditions from which we emerged. To truly appreciate the elegance of this idea, we must delve deeper into the nature of the black hole's interior, moving beyond the simple, non-rotating Schwarzschild solution to the more realistic Kerr metric for a spinning black hole. Most black holes in the universe are spinning, and the Kerr solution introduces an even more bizarre possibility. The singularity is not a point, but a ring singularity. This ring singularity is a one-dimensional ring of zero thickness and infinite density. More importantly, the Kerr metric allows for the possibility of a traversable wormhole that connects the interior of the black hole to another region of space-time, or even another universe. In the context of the black hole cosmology, the matter that collapses into the parent black hole is not just crushed, but is funneled through this Kerr-like wormhole structure. The matter, now subject to the immense torsion of the Einstein-Cartan theory, bounces and begins its expansion. The key difference between the parent universe and the baby universe is the direction of time. From the perspective of the parent universe, the matter is falling in and time is moving forward. From the perspective of the baby universe, our universe, the matter is moving out, and time is also moving forward. The wormhole acts as a one-way valve, a cosmic filter that allows matter to enter but never to return. This brings us to the concept of the white hole. In general relativity, a white hole is the time-reversed solution of a black hole. Just as a black hole is a region from which nothing can escape, a white hole is a region into which nothing can enter. While black holes are common, white holes have never been observed, and most physicists consider them to be purely theoretical. However, in the black hole cosmology model, the interior of the parent black hole, after the bounce, is mathematically equivalent to a white hole. The matter that bounced is now expanding outward, and the boundary of our universe, the cosmological horizon, is acting like the event horizon of a white hole, preventing anything from the parent universe from entering. We are, in a sense, living inside a white hole that was born from a black hole. This duality is a beautiful symmetry that suggests a fundamental connection between the beginning and the end of cosmic structures. The black hole is the cosmic eater, and the white hole is the cosmic spitter, and we are the material that was spat out. The idea of a universe born from a black hole is not entirely new. It has echoes in the work of the Russian-American physicist Igor Novikov and the Israeli physicist Jacob Bekenstein, who explored the thermodynamics of black holes. Bekenstein proposed that black holes have entropy, a measure of disorder, which is proportional to the area of their event horizon. This was a radical idea, as entropy is a property of matter, and black holes were thought to be regions of pure space-time. Bekenstein's work, later refined by Stephen Hawking, led to the discovery of Hawking radiation, the faint thermal radiation that black holes are predicted to emit. Hawking radiation suggests that black holes are not truly black, but slowly evaporate over vast timescales. The black hole cosmology model builds on this foundation by suggesting that the information paradox is resolved not by the destruction of information, but by its transfer. The information that falls into the black hole is not lost to the parent universe, but is encoded in the initial conditions of the baby universe. This transfer of information is a form of cosmic recycling, ensuring that the fundamental laws of physics are preserved across the boundary of the event horizon. This means that the entire history of the parent universe, in a highly compressed and encoded form, is what determined the initial conditions of our own universe. Every galaxy, every star, every atom in our body is a direct descendant of the matter that collapsed in the parent universe. To truly grasp the scale of this idea, we must return to the concept of the parent universe. If our universe is a black hole, what is the parent universe like? It must be a universe that is capable of forming black holes large enough to contain our entire observable cosmos. Our universe is estimated to be about 93 billion light-years across. The Schwarzschild radius of a black hole is directly proportional to its mass. To have an event horizon the size of our universe, the parent black hole would need to have a mass equivalent to about 10 to the power of 23 solar masses. This is an unimaginably large mass, far exceeding the mass of any known supercluster of galaxies. This requirement suggests that the parent universe must be vastly larger and older than our own. It might be a universe that has undergone many cycles of star formation, collapse, and black hole creation. The existence of such a massive black hole in the parent universe is a necessary condition for the black hole cosmology model to be viable. It forces us to confront the possibility of a multiverse, not just a collection of separate, disconnected universes, but a nested hierarchy of universes, with each black hole serving as a seed for the next generation. This is a fractal universe, where the largest structures are mirrored in the smallest, and the cosmos is a never-ending cycle of collapse and rebirth. The concept of a nested multiverse, where black holes are the cosmic seeds, is known as cosmological natural selection, a theory proposed by the physicist Lee Smolin. Smolin suggested that the fundamental constants of physics, the speed of light, the strength of gravity, the mass of the electron, are not arbitrary, but are tuned to maximize the production of black holes. Universes that produce more black holes are more likely to reproduce, creating baby universes with slightly different constants. Over vast timescales, this process would lead to a natural selection of universes, favoring those that are most efficient at black hole formation. Our universe, with its abundance of stars and galaxies, is perfectly tuned for black hole production, suggesting that it is a successful descendant in this cosmic evolutionary process, the black hole. Cosmology model provides a physical mechanism for Smolin's theory. The wormhole at the center of the black hole is the reproductive organ of the universe, and the torsion field is the genetic material that determines the initial conditions of the baby universe. The constants of physics in the baby universe are a function of the matter that collapsed into the parent black hole and the immense energy of the bounce. This is a truly revolutionary idea, one that connects the smallest scales of quantum mechanics, the spin of elementary particles, to the largest scales of cosmology, the structure and evolution of the entire cosmos. It suggests that the universe is not a random accident, but a finely tuned machine for the production of black holes, and ultimately for the creation of new life. Let us now turn our attention to the observational tests of this theory. How can we, from within our black hole universe, prove or disprove this radical hypothesis? The key lies in the subtle differences between the predictions of the black hole cosmology model and the standard Big Bang model. One crucial difference is the prediction of cosmic rotation. The standard Big Bang model, based on the Friedmann-Lemaitre-Robertson-Walker FLRW metric, assumes that the universe is perfectly isotropic and homogeneous, the same in all directions and at all locations. This assumption is supported by the near-perfect uniformity of the cosmic microwave background, CMB. However, the black hole cosmology model, which is based on the collapse of a rotating star in the parent universe, predicts a slight, residual rotation in our universe. This rotation would be extremely small, but it might be detectable in the subtle patterns of the CMB or the alignment of galaxies. In 2010, Popławski and his colleagues published a paper suggesting that the observed preferred direction in the alignment of quasars and the polarization of the CMB could be a subtle signature of this cosmic rotation. While the evidence is not conclusive, it is a tantalizing hint that our universe may not be as perfectly uniform as the standard model assumes. The search for cosmic rotation is an active area of research, and future, more precise measurements of the CMB and the large-scale structure of the universe could provide the definitive test. If we find a statistically significant, non-random alignment of cosmic structures, it would be a powerful piece of evidence for the black hole cosmology model. Another potential test lies in the nature of dark matter. Dark matter is the mysterious, invisible substance that makes up about 85% of the matter in the universe. It does not emit or absorb light, but its gravitational effects are clearly visible in the rotation curves of galaxies and the clustering of galaxy clusters. The standard model requires the existence of a new, exotic particle, the weakly interacting massive particle, WIMP, to account for dark matter. Despite decades of searching, WIMPs have not been detected. The black hole cosmology model offers an alternative explanation. The immense energy of the bounce, combined with the extreme curvature and torsion, could have created a vast amount of sterile neutrinos or other exotic particles that behave like dark matter. The torsion field itself could also be the source of a non-particle form of dark matter. This is a complex area of research, but the possibility that the black hole's interior naturally generates the necessary amount of dark matter is a powerful argument in favor of the theory. The dark matter we observe might not be an exotic particle from the early universe, but a relic of the immense gravitational forces that created our universe. The most direct test, however, would be the detection of primordial black holes with masses far smaller than those formed by stellar collapse. In the black hole cosmology model, the extreme conditions of the bounce could have created a spectrum of black holes, ranging from microscopic to supermassive. The detection of these primordial black holes, perhaps through their gravitational wave signatures, would be a strong piece of evidence for the non-singular bounce and the torsion-driven expansion. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, and its European counterpart, Virgo, are constantly searching for these gravitational ripples, and a unique signature from a primordial black hole could be the smoking gun that confirms the black hole universe hypothesis. Let us now take a step back and consider the philosophical implications of this theory. If our universe is a black hole, it means that our existence is fundamentally linked to the death of a star in another universe. The matter that makes up our bodies, our planet, and our stars is the recycled remnants of a cosmic collapse. This is a profound and humbling thought, one that connects us to the largest and most violent events in the cosmos. We are, quite literally, stardust that has been through a cosmic washing machine. The theory also offers a unique perspective on the arrow of time. In our universe, time flows in one direction, from the past to the future. This is known as the thermodynamic arrow of time, and it is linked to the increase of entropy. In the black hole cosmology model, the arrow of time is set by the expansion of the baby universe. The expansion is a process of increasing disorder, and the flow of time is simply the consequence of this cosmic expansion. The parent universe, which is collapsing, would have an opposite arrow of time, with entropy decreasing and time flowing backward. This is a highly speculative idea, but it suggests that the fundamental nature of time is not a universal constant, but a local property of each universe, determined by its state of expansion or collapse. Time, in this view, is not an absolute, but a relative concept, a consequence of the universe's geometry. The black hole cosmology model is a powerful example of how a single, radical idea can connect seemingly disparate areas of physics. It links the geometry of space-time, general relativity, to the quantum properties of matter, spin and torsion, and it offers a unified explanation for the Big Bang, cosmic inflation, dark energy, and dark matter. It is a theory that is both elegant and testable, and it represents a major step forward in our quest to understand the ultimate nature of reality. It is a theory that suggests that the universe is not a random accident, but a finely tuned machine for the production of black holes, and ultimately for the creation of new life. To fully grasp the scale of this theory, we must return to the concept of the event horizon. For us, living inside the black hole, the event horizon is the cosmological horizon, the boundary of the observable universe. We can never cross it, and we can never see what lies beyond it. From the perspective of the parent universe, the event horizon is a one-way membrane, a cosmic filter that allows matter to enter but never to return. This is the ultimate prison, a cosmic cage that contains our entire existence. But this prison is also a cradle. The black hole is not a region of pure destruction, but a cosmic womb that gives birth to new universes. The collapse of a star in the parent universe is the necessary condition for the creation of our own. This is a profound paradox, one that suggests that creation and destruction are two sides of the same cosmic coin. The death of one universe is the birth of another, and the cycle of cosmic evolution is eternal. The black hole cosmology model is still a work in progress, and it faces many challenges. The most significant challenge is the lack of direct observational evidence for the effects of torsion. The Torsian field is extremely weak in the low-density environment of our universe, and its effects are difficult to measure. Future experiments, such as more precise measurements of the gravitational field around massive objects, could provide the necessary evidence. Another challenge is the need to reconcile the theory with the principles of quantum gravity. The black hole cosmology model is based on the Einstein-Cartan theory, which is a classical theory of gravity. A complete theory of the universe, one that can fully describe the conditions at the bounce, will require a quantum theory of gravity, such as loop quantum gravity or string theory. The integration of the black hole cosmology model with these quantum theories is an active area of research, and it promises to reveal even deeper connections between the black hole and the universe. The ultimate question remains: are we truly living inside a black hole? The answer, for now, is a resounding maybe. The theory is mathematically sound. It offers elegant solutions to some of the most profound mysteries of cosmology, and it is potentially testable. It is a testament to the power of human curiosity and the relentless pursuit of knowledge. The universe is a far stranger and more beautiful place than we can ever imagine, and the black hole, the ultimate symbol of cosmic destruction, may be the key to understanding the ultimate nature of creation. The journey we have taken today, from the basic principles of general relativity to the cutting-edge theories of black hole cosmology, is a reminder that the universe is not a static, finished product, but a dynamic, evolving system. Our understanding of reality is constantly being challenged and refined, and the next great discovery may be just around the corner. We have explored the possibility that our universe is a black hole, a cosmic womb that gives birth to new realities. We have seen how the principles of torsion and the non-singular bounce can resolve the singularity problem and the information paradox. We have examined the observational evidence from the cosmological horizon to the subtle rotation of the cosmos, and we have considered the philosophical implications of a nested multiverse where creation and destruction are eternally linked. The story of the black hole is the story of the universe, and the story of the universe is the story of us. We are the children of a cosmic collapse, the matter that bounced back from the brink of oblivion. Our existence is a testament to the power of the laws of physics, and our curiosity is the engine that drives the endless quest for knowledge. To truly appreciate the radical nature of the black hole cosmology model, we must first confront the absolute certainty of the singularity within the framework of general relativity. This certainty comes from the groundbreaking work of Roger Penrose and Stephen Hawking in the 1960s and 70s, encapsulated in the Penrose-Hawking singularity theorems. These theorems are not about the specific mechanism of collapse, but rather a powerful geometric proof that under very general and reasonable conditions, namely that gravity is always attractive, and that matter has positive energy density. A singularity is an inevitable consequence of gravitational collapse. Before their work, physicists often hoped that some unknown physical process, perhaps a stabilizing force or a complex rotation, would prevent the final collapse to a point. The theorems crushed this hope. Penrose proved that once a trapped surface forms, a surface from which all light rays converge inward, which is essentially the event horizon, the collapse to a singularity is unavoidable. Hawking later extended this to show that the universe itself must have begun from a singularity, the Big Bang singularity. The singularity, therefore, is not a flaw in the equations. It is a fundamental prediction. It is the point where the classical theory of gravity reaches its limit. The equations of general relativity, which describe the smooth, continuous geometry of space-time, simply cannot handle the infinite curvature and density at that point. They predict their own demise. This is the crisis of the singularity. It is a mathematical dead end that screams for a new theory of physics, a theory of quantum gravity, to take over. The black hole cosmology model, by introducing the repulsive force of torsion, is essentially an attempt to modify the conditions of the Penrose-Hawking theorems, specifically by introducing a form of matter, the spinning particles, that can exert a negative pressure, thus preventing the formation of the final, crushing singularity. It replaces the inevitable collapse with an inevitable bounce. Let us delve deeper into the concept of torsion. In general relativity, the geometry of spacetime is described by the metric tensor, which tells us about curvature. In the Einstein-Cartan theory, a second geometric object, the torsion tensor, is introduced. While curvature is related to the symmetric part of the connection, torsion is related to the antisymmetric part. Think of a piece of paper. If you bend it, you create curvature. If you twist it, you create torsion. In general relativity, space-time is only bent. In Einstein-Cartan theory, it can be bent and twisted. The crucial insight of the Einstein-Cartan theory is that this twisting, this torsion, is not an arbitrary feature of space-time, but is directly sourced by the spin of matter. Every fundamental particle, electrons, quarks, neutrinos, possesses an intrinsic angular momentum, a quantum mechanical property called spin. This spin is quantized, meaning it can only take on discrete values. In the BHC model, as matter collapses, the density becomes so extreme that the spins of all these particles align and interact coherently. This collective spin generates the torsion field. The torsion field, in turn, acts back on the matter. It couples to the spin of the particles, creating a repulsive force that is proportional to the square of the matter density. This is a nonlinear effect that only becomes significant at densities far exceeding the nuclear density of a neutron star. This is the mechanism that prevents the singularity. The universe, in this view, is not just a passive stage for matter and energy. It is an active, dynamic medium where the fundamental quantum property of spin can geometrically alter the fate of the cosmos. The universe saves itself from infinite collapse by leveraging the quantum nature of its smallest constituents. The Kerr metric, which describes a rotating black hole, is a far more complex and fascinating solution than the simple Schwarzschild black hole. The rotation introduces a region called the ergosphere, a space outside the event horizon where space-time is dragged around so violently that it is impossible to remain stationary. Anything entering the ergosphere is forced to rotate with the black hole. This is the frame dragging effect, a direct consequence of general relativity. Inside the event horizon of a Kerr black hole, the singularity is not a point, but a ring. This ring singularity is a one-dimensional loop of infinite density. The most mind-bending feature of the Kerr solution is that it mathematically allows for the possibility of passing through the ring singularity and emerging into another region of spacetime, which could be a different universe. This is the theoretical basis for the wormhole in the BHC model. However, this possibility immediately raises the spectre of the cosmic censorship hypothesis, proposed by Roger Penrose. This hypothesis states that every singularity formed by gravitational collapse must be hidden behind an event horizon. If a singularity were exposed, a naked singularity, it would violate the predictability of physics, as the laws of physics break down at the singularity, and an observer could see the breakdown. The BHC model, by replacing the singularity with a non-singular bounce, effectively bypasses the need for cosmic censorship. It ensures that the physics remains predictable, even at the point of maximum compression, because the density remains finite. The black hole is no longer a region of unpredictable chaos, but a predictable, albeit extreme, cosmic transformer. The black hole cosmology model offers a powerful, non-anthropic solution to one of the most vexing problems in modern physics, the fine-tuning problem. This problem asks why the fundamental constants of nature, the strength of the electromagnetic force, the mass of the electron, the cosmological constant, are so perfectly tuned to allow for the existence of stars, galaxies, and life. If the strength of the strong nuclear force were even slightly different, carbon could not form. If the cosmological constant were a tiny bit larger, the universe would have expanded too quickly for galaxies to form. It seems almost as if the universe was designed for us. The traditional response to this is the anthropic principle, which states that the universe must be the way it is, because if it were not, we would not be here to observe it. While logically sound, it is scientifically unsatisfying. The BHC model, combined with cosmological natural selection, CNS, provides a dynamic, evolutionary explanation. The CNS theory posits that universes reproduce through black holes. Universes that are more efficient at forming black holes, which requires a specific set of physical constants, will have more offspring universes. Over countless cycles of collapse and bounce, the constants of nature are naturally selected to favor black hole production. Our universe, with its perfect balance of forces that allows for long-lived stars and the formation of heavy elements, is a universe that is extremely good at making black holes. Therefore, we live in a universe that is a successful descendant in this cosmic evolutionary process. The fine-tuning is not a coincidence or a design. It is the result of an infinite, self-reproducing cosmic machine. The constants of nature are not arbitrary. They are the inherited traits of a successful cosmic lineage. This shifts the question from "why are the constants so perfect?" to "how did the constants evolve to be so perfect?" A much more scientifically tractable question. The cosmic microwave background, the faint afterglow of the Big Bang, is the most powerful piece of evidence supporting the standard cosmological model. Its near-perfect uniformity confirms that the early universe was incredibly smooth and homogeneous. However, the CMB also contains tiny temperature fluctuations, the seeds of all the galaxies and clusters we see today. In the standard model, the uniformity of the CMB is explained by cosmic inflation, a period of exponential expansion in the first fraction of a second of the universe. Inflation stretches the universe so rapidly that any initial irregularities are smoothed out, and the quantum fluctuations are stretched to cosmic scales, becoming the seeds of structure. The black hole cosmology model offers an alternative, more natural explanation. The matter that forms our universe is the highly compressed, homogenized matter from the collapsing parent star. The immense pressure and density at the non-singular bounce would naturally lead to a state of near-perfect uniformity. The tiny fluctuations in the CMB could be the result of the quantum fluctuations of the torsion field itself at the moment of the bounce, or the residual inhomogeneities of the matter that collapsed. Furthermore, the BHC model naturally explains the flatness of the universe, a key feature inferred from the CMB. The immense repulsive force of torsion at the bounce drives a rapid expansion that is mathematically equivalent to the inflationary period, but without the need for the hypothetical inflaton field. The universe is flat because the initial conditions of the bounce naturally produce a flat geometry. The BHC model, therefore, provides a more unified and elegant explanation for the initial conditions of the universe, rooted in the known properties of matter and gravity, rather than an arbitrary, hypothetical field. The black hole cosmology model has a direct, testable prediction regarding the existence of primordial black holes, PBHs. In the standard model, PBHs are a theoretical possibility, formed from the collapse of extremely dense regions in the very early universe. In the BHC model, however, the extreme conditions of the non-singular bounce, the immense pressure and density, would naturally lead to the formation of a wide spectrum of PBHS, ranging from microscopic to supermassive. These PBHs could be the long sought-after dark matter. If a significant fraction of dark matter is composed of PBHs, it would eliminate the need for the hypothetical WIMP particle. The gravitational effects of these PBHs would explain the rotation curves of galaxies and the clustering of galaxy clusters. The BHC model provides a physical mechanism for the formation of these PBHs, linking the dark matter mystery directly to the birth of our universe. The search for PBHs is an active area of research. The Laser Interferometer, Gravitational Wave Observatory, LIGO, and the Virgo Interferometer are constantly searching for the gravitational wave signatures of black hole mergers. If a merger of two very small black holes is detected, it would be a strong piece of evidence for the existence of PBHS and a powerful, indirect confirmation of the black hole cosmology model. The BHC model, therefore, is not just a philosophical curiosity. It is a scientifically testable hypothesis that could revolutionize our understanding of the universe. The black hole cosmology model paints a picture of a universe that is not a one-off event, but a part of an infinite, self-reproducing cycle. The death of a star in the parent universe is the birth of our universe. The matter that makes up our bodies, our planet, and our stars is the recycled remnants of a cosmic collapse. This is the ultimate cosmic recycling program, where creation and destruction are eternally linked. This concept of an eternal universe is a profound philosophical shift. The standard Big Bang model suggests a beginning of time, a moment of creation from nothing. The BHC model suggests that the universe is eternal, cycling through periods of collapse and expansion, with each black hole acting as a portal to the next cycle. This eliminates the need for a creator or a beginning of time, offering a purely scientific explanation for the existence of the cosmos. The universe, in this view, is a fractal, a self-similar structure where the largest cosmic events, the collapse of a star, are mirrored in the creation of a new universe. The black hole, the ultimate symbol of cosmic destruction, is revealed to be the ultimate cosmic womb. This is the final, most awe-inspiring conclusion of the black hole cosmology model. Our universe is not a prison, but a cradle, a testament to the infinite, self-renewing power of the cosmos. The ultimate question remains: are we truly living inside a black hole? The answer, for now, is a resounding maybe. The theory is mathematically sound. It offers elegant solutions to some of the most profound mysteries of cosmology. And it is potentially testable. It is a testament to the power of human curiosity and the relentless pursuit of knowledge. The universe is a far stranger and more beautiful place than we can ever imagine. And the black hole, the ultimate symbol of cosmic destruction, may be the key to understanding the ultimate nature of creation. The journey we have taken today, from the basic principles of general relativity to the cutting-edge theories of black hole cosmology, is a reminder that the universe is not a static finished product, but a dynamic, evolving system. Our understanding of reality is constantly being challenged and refined, and the next great discovery may be just around the corner. We have explored the possibility that our universe is a black hole, a cosmic womb that gives birth to new realities. We have seen how the principles of torsion and the non-singular bounce can resolve the singularity problem and the information paradox. We have examined the observational evidence from the cosmological horizon to the subtle rotation of the cosmos, and we have considered the philosophical implications of a nested multiverse, where creation and destruction are eternally linked. The story of the black hole is the story of the universe, and the story of the universe is the story of us. We are the children of a cosmic collapse, the matter that bounced back from the brink of oblivion. Our existence is a testament to the power of the laws of physics, and our curiosity is the engine that drives the endless quest for knowledge. Let us now deepen our understanding of the cosmic stage, the very fabric of space-time, and how our human intuition fails us at the extremes of gravity. General relativity, as we established, is a geometric theory. It replaces the Newtonian concept of a force with the curvature of a four-dimensional manifold. But what does it truly mean for spacetime to be curved? It means that the shortest distance between 2 points, a geodesic, is not a straight line, but a curve. On Earth, a plane flying from New York to Tokyo follows a curved path on a flat map, but on the spherical surface of the Earth, it is the shortest, most direct route. In the presence of a massive object like a black hole, the curvature is so extreme that all paths lead inward. Imagine a river flowing faster and faster. At a certain point, the current is so strong that even if you paddle your boat as fast as the speed of light, you can make no headway against the current. You are swept downstream. The event horizon is precisely this point in the river of space-time. Inside, the flow of space toward the singularity is faster than the speed of light. This is the profound, almost poetic realization that general relativity forces upon us. The event horizon is not a wall of infinite gravity, but a boundary where the nature of space and time fundamentally changes. Inside the event horizon, the radial coordinate, the direction pointing toward the center, becomes a time-like coordinate, and the time coordinate becomes a space-like coordinate. This is not a metaphor. It is a mathematical reality. What does this mean for you, the intrepid explorer who has crossed the boundary? It means that moving toward the singularity is as inevitable as moving toward tomorrow. You cannot choose to stop moving inward any more than you can choose to stop time. The singularity is your future, a fixed point in your personal timeline. And escaping the black hole is as impossible as traveling backward in time. This is the cosmic horror of the black hole's interior, a region where the familiar concepts of space and time are utterly inverted, leading to the inescapable doom of the singularity. The singularity itself, that point of infinite density, is where the equations of general relativity cease to function. They produce an infinity, a mathematical error message. This is the ultimate signpost in physics, telling us that our current theory is incomplete. It is a crisis that demands a new physics, a theory that can seamlessly blend the smooth, continuous geometry of space-time with the discrete, probabilistic nature of the quantum world. This is the quest for quantum gravity, and it is the quest that the black hole cosmology model attempts to fulfill. To understand the solution offered by the black hole cosmology model, we must first understand the scale at which the problem occurs, the Planck scale. This is the realm where the effects of quantum mechanics and gravity become equally important. The Planck length is the smallest possible distance, approximately 10 to the power of negative 35 meters. The Planck time is the shortest possible time interval, about 10 to the power of negative 43 seconds. These are not just small numbers. They represent the fundamental granularity of the universe. Below the Planck length, the very concept of smooth, continuous space-time breaks down. At the singularity, all the matter of the collapsed star is compressed into a region smaller than the Planck length. Here, space-time is no longer a smooth, four-dimensional manifold, but a chaotic, bubbling froth known as quantum foam. This is the realm where the uncertainty principle reigns supreme, and the geometry of space-time is constantly fluctuating. General relativity, which assumes a smooth, classical space-time, is simply inadequate to describe this environment. The black hole cosmology model, rooted in the Einstein-Cartan theory, provides a bridge to this quantum realm by incorporating the quantum property of spin into the gravitational equation. Every elementary particle, electrons, quarks, neutrinos, has an intrinsic angular momentum, a quantum mechanical spin. This spin is a fundamental property, as real as mass or charge. In the vast, empty stretches of space, the effects of this spin are negligible, but as matter collapses into a black hole, the density increases exponentially, and the collective spin of all these particles begins to interact coherently. Imagine a vast crowd of people, all spinning in place. When they are far apart, their individual spins don't affect the crowd. But when they are packed shoulder to shoulder, their collective spinning creates an immense outward pushing pressure. This is the repulsive force of torsion. This force is a direct consequence of the quantum mechanical spin of matter, now manifesting as a geometric property of space-time. It is a form of quantum gravity, a natural consequence of including the quantum nature of matter into the gravitational equation. This repulsive force is the key to avoiding the singularity. Instead of being crushed to a point of infinite density, the matter reaches a maximum, finite density, the non-singular bounce. At this point, the repulsive force of torsion overwhelms the attractive force of gravity, and the matter begins to expand rapidly. This is the big bounce, the moment of creation of our universe. The singularity is replaced by a quantum bridge, a transition from a contracting phase to an expanding phase. The universe is eternal, cycling through periods of collapse and expansion, with each black hole acting as a portal to the next cycle. The black hole information paradox is one of the deepest and most persistent puzzles in theoretical physics. It pits the two great pillars of modern physics, general relativity and quantum mechanics, against each other. General relativity, through the no-hair theorem, suggests that information is lost when it falls into a black hole. Quantum mechanics, through the principle of unitarity, insists that information can never be truly lost. The paradox deepens with Hawking radiation. Stephen Hawking showed that black holes are not truly black, but slowly radiate away their mass in the form of thermal particles. This radiation is purely thermal, carrying no information about the matter that fell in. If the black hole eventually evaporates completely, the information is gone forever, violating unitarity. This is a fundamental conflict that suggests our understanding of physics is incomplete. The black hole cosmology model offers a radical resolution. The information is not lost, it is transferred. The information that falls into the black hole is carried through the wormhole and becomes the initial matter and energy of the new, expanding universe. The black hole is not a cosmic dead end, but a cosmic reproductive mechanism. The information is preserved, not by being radiated away, but by being transferred to a new reality. This idea is deeply connected to the holographic principle, a concept that suggests that all the information contained in a volume of space can be encoded on the two-dimensional surface that bounds that region. In the context of a black hole, this means that all the information about the matter that fell in is encoded on the event horizon. The BHC model provides a physical mechanism for this information to be transferred to the new universe, rather than just stored on the surface. The information is the genetic material of the baby universe, determining its initial conditions and the fundamental constants of nature. The black hole cosmology model is not just a theoretical curiosity. It makes testable predictions that differ from the standard Big Bang model. One of the most intriguing is the prediction of cosmic rotation. The standard model assumes the universe is perfectly isotropic and homogeneous, the same in all directions. This is supported by the near-perfect uniformity of the cosmic microwave background, CMB. However, the BHC model, born from the collapse of a rotating star in the parent universe, predicts a slight residual rotation in our universe. This rotation would be extremely small, but it might be detectable in the subtle patterns of the CMB. The observed anisotropies in the CMB, particularly the so-called axis of evil, a statistically improbable alignment of the CMB's largest features, could be a subtle signature of this cosmic rotation. This axis of evil is a persistent anomaly in the CMB data, a preferred direction in the universe that contradicts the standard model's assumption of perfect isotropy. The BHC model offers a natural explanation. The axis of evil is the cosmic echo of the rotation of the parent black hole. The search for cosmic rotation is an active area of research. Future, more precise measurements of the CMB and the large-scale structure of the universe could provide the definitive test. If we find a statistically significant, non-random alignment of cosmic structures, it would be a powerful piece of evidence for the black hole cosmology model. The black hole cosmology model offers a unified explanation for the two greatest mysteries of modern cosmology: dark matter and dark energy. Dark matter. The standard model requires the existence of a new, exotic particle, the WIMP, to account for dark matter. The BHC model offers an alternative: the immense energy and extreme conditions of the non-singular bounce could have naturally created a vast amount of primordial black holes, PBHs. These PBHs, ranging from microscopic to supermassive, could account for a significant fraction of dark matter, eliminating the need for the hypothetical WIMP particle. Furthermore, the residual effects of the torsion field itself could manifest as a non-particle form of dark matter, providing the extra gravitational pull observed in galaxies. Dark energy. The accelerated expansion of the universe is driven by dark energy, a mysterious force that behaves like a cosmological constant. The BHC model provides an elegant solution. The torsion field, which is responsible for the bounce, can contribute to the energy density of the vacuum. The residual effects of the immense torsion from the bounce could be the subtle, pervasive force that is now pushing our galaxies apart. The dark energy we observe is simply the lingering effect of the immense physics that gave birth to our universe, a natural consequence of the Einstein-Cartan theory, not an arbitrary constant. The journey we have taken today, from the basic principles of general relativity to the cutting-edge theories of black hole cosmology, is a reminder that the universe is not a static, finished product, but a dynamic, evolving system. Our understanding of reality is constantly being challenged and refined, and the next great discovery may be just around the corner. We have explored the possibility that our universe is a black hole, a cosmic womb that gives birth to new realities. We have seen how the principles of torsion and the non-singular bounce can resolve the singularity problem and the information paradox. We have examined the observational evidence from the cosmological horizon to the subtle rotation of the cosmos, and we have considered the philosophical implications of a nested multiverse, where creation and destruction are eternally linked. The story of the black hole is the story of the universe, and the story of the universe is the story of us. We are the children of a cosmic collapse, the matter that bounced back from the brink of oblivion. Our existence is a testament to the power of the laws of physics, and our curiosity is the engine that drives the endless quest for knowledge. Thank you for joining us on this journey into the cosmo depth. We hope you will continue to explore the mysteries of the universe with us. Until next time, keep looking up and keep questioning everything.